Hello everyone. Today we're going to be talking about the rectangular approximation method, or Riemann sums. This presentation is done by Johnny Ocampo, Christian Salgado, Eddie Cazada, and Herman Garcia.
All right, so let's start off with what is RAM? So it's a method of approximating area under a graph by drawing rectangles under a curve. And this particular method is pretty useful because it's easier to calculate areas of rectangles and curves. I'm sure you guys could agree. It's a lot easier to calculate rectangles because we learned that in elementary school. And the more subintervals or rectangles that you use, the more accurate the approximation. And we'll see an example of this once we get into MRAM because the answer is slightly off because of the low amount of subintervals we've used. There are three methods of RAM: LRAM, MRAM, and RRAM. And you can see that on the pictures on the right. If f is a positive continuous function increasing function on the interval a to b, then LRAM would be a slight underestimate and RM will be a slight overestimate. And that's just seen through the positive continuous increasing functions on the right. And yeah.
So LRAM is basically just a method of approximating area under a graph that uses rectangles whose height is the y value of the left endpoint of the subintervals. And this typically does provide an underestimation as chunks under the graph are left out, but that is not always the case. And then RM is pretty similar, however, it just uses rectangles whose height is the y value of the right endpoint of the subintervals. And this typically provides an overestimation as there's excess chunks over the curve, but once again, that's not always the case. So this is just a sample, an LRAM sample. And so the problem says a tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for AH are given in the table above. And then the question says, use a left Riemann sum with three subintervals indicated by the data on the table to approximate the volume of the tank and then indicate units of measure. So the first thing I did in this problem was I drew a graph just because it's kind of confusing since the x-axis is height in feet and then the y-axis is the area in feet. And then next I just made a little table so I wouldn't get confused. And so the three intervals that they gave us are from 0 to 2, 2 to 5, and from 5 to 10. And then so the width of those intervals, the first one's going to be 2, the second one's going to be 3, and the last one's 5. And then the height based on the left endpoint of the subintervals are 50.3, 14.4, and 6.5. And then the area, which we just multiply those two together to get, is are 100.6, 43.2, and 32.5. And then some of those areas are equal to 176.3 feet cubed, cubic feet, since it is asking for the volume. And then yeah, that's the answer. Pretty similar. It's just using a right Riemann sum to do the same thing. And so the question says a tank contains 50 liters of oil at time t equals 4 hours. Oil is being pumped into the tank at a rate of RT, where RT is measured in liters per hour and T is measured in hours. Selected values of RT are given in the table above. Using a right Riemann sum with three subintervals and data from the table, what is the approximation of the numbers of liters of oil that are in the tank at time t equals 15 hours? And so this is basically the same thing. I use the same table to do it. And so the three intervals are from 4 to 7, 7 to 12, and from 12 to 15. And the widths are 3, 5, and 3. And the heights using the right endpoints of the subintervals and rectangles are 6.2, 5.9, and 5.6. And then the areas are 18.6, 29.5, and 16.8, which all equal 64.9. However, in this problem, it does say, if you look back at the question, that the tank contains 50 liters of oil at the time t equals 4. So it's kind of an initial condition. So to find the total area, you have to add 64.9 plus 50, which gives you 114.9 liters.
All right. We're going to move on to MRAM. And this method uses rectangles whose height is the y value of the midpoint of the subintervals. And you can see like those little dots in between the rectangles on the right-hand side. And MRAM is typically the most accurate RAM method. And except for continuous functions, all three estimates are equal. So you could think about it as like a horizontal line at like y equals 5. If you were to do LRAM, RRAM, and MRAM, it would just be the same answer because all values are the same. You can calculate the width of rectangles by b minus a over n, as we previously stated, and the height is now y value at x equals b plus a over 2. All right, so we're gonna do an MRAM sample. We couldn't really find like any good like AP questions that we found for LRAM and RRAM. So I just wanted to do this problem just to get the point across to you guys because I'm sure you guys already got the gist of it. So it's use MRAM to approximate the value of the area under the graph of y equals square or y equals x squared from 0 to 8 using 4 subintervals. And that little rectangle I drew in my work is the formula that we gave you guys to find the width of the subintervals. B minus a, so it'd be 8 minus 0 equals 8. And then the amount of subintervals, like we said earlier, is 4. So a divided by 4 is equal to 2. And then essentially, when we're trying to find the area, it's just like when you're trying to find the midpoint of anything. You add those two values together and divide by 2. So in between of each subinterval, we got 1, 3, 5, and 7. And then you basically plug in those x values into our original function, y equals x squared, and you get those values in the parentheses, the 1 plus 9 plus 25 plus 49. And you can't forget about the 2. We're leaving the 2 because we're multiplying the width of the subintervals by the actual values of the midpoints. Once you do all that, it's going to be 2 times 84, and that's 168. And like I said earlier, you are going to get a little bit of a rough estimate when you do such a low amount of subintervals. In this case, we only did 4. And on the bottom right, we see the actual answer of 170.7. And that's just due, I mean, if we wanted to get a more of exact answer, we could have done more subintervals.
Okay, so next we're going to be talking about the trapezoidal rule. So to recap, a Riemann sum is an approximation of the area under a curve by dividing it into multiple simple shapes. An example of one of those simple shapes we can use is a trapezoid. So surprisingly, the trapezoidal method is the most accurate. As you can see the graph down here in the bottom, by drawing trapezoid shapes you can kind of connect the curve a little better to give you more of an accurate approximation. So you can see the formula down here for the trapezoidal rule once that moves right now. You have the height divided by 2 times, so a way to think about this is your first and last values in your subinterval are not going to be multiplied by 2, but every other value in between will. So you can see the y0 plus 2 times y1 plus 2 times y2 all the way until you eventually reach plus y sub n, where you see that isn't multiplied by 2 anymore. So essentially this is just drawing trapezoids, finding the areas of those. I'm sure you know the formula for the area of a trapezoid is the sum of its bases divided by 2 times its height. It's the same thing here, only we're summing all of them to find the area under the curve. So, that's a lot to take in, so we're going to look at a sample problem. So, the same thing, we couldn't really find a very good AP problem for this, so we just decided to find an example that would give you a good understanding of what the trapezoidal is and how it works. So it says use the trapezoidal rule with n equals 4 to approximate the value of the definite integral from 0 to pi of sine of x dx. So you can see on the leftmost picture, we have just the typical sine graph. You can see, I'm sure most of you are familiar with it. But then on the right is where I start to do my work with it. So from 0 to pi, you just get that top part, the positive part, and that's all we're going to have to worry about for now. So we're going to calculate the width of each rectangle, same formula as before. We did b minus a, so pi minus 0, which is just pi over n, which in this case 4 subintervals, so 4. We end up with pi over 4. So you see for the formula, you have t equals h divided by 2. So you can see my work. I did pi over 4 times 1/2, which ends up as pi over 8. And then my y0, of course we know that the sign of 0 is going to be 0. And then all the way at the end, my y sub n, we know that the sign of pi is also 0. And everything in between, we do 2 times y1, which is pi over 4, so we get radical 2 over 2. And then we do 2 times the sine of pi over 2, which is just 1, so we have that 1 there. And then we have 2 times the sine of 3 pi over 4, which is just radical 2 over 2. And once you end up doing all the work, you end up with pi over 8 times 2 plus 2 radical 2, which approximates to 1.896. So this method gives you close to accurate answers. You get a better estimation with using this method than with the other methods. So, thank you for watching. Our famous man Riemann said that. If you have any questions, be sure to let us know.